All right, so you have a homework assignment due today, but we're a little bit behind in the material, so I think I'm going to give you an extra 24 hours, okay? So you can do this, you can have this stuff in tomorrow. And good. And then because I think we had some greatest lower bound, least upper bound stuff, and so we'll cover that material today, and then let you hand it in tomorrow. But anyway, you had some. Did you have a question that you think we might answer it later? Or? Oh, that's right. I see. The question is.
It's related to itself.
Yeah. The question is when you draw a Hassel diagram, like if this is A, and if you have the ordered pair A. Yeah. You don't do a loop like that. If it's related to itself, there's no way to show. Yeah. There's no way to show that AA on the Hassel diagram.
There's another one.
Good question.
With anything else.
Okay, so all right.
Yeah,
So next question. I see. Yeah. Got it. Okay. So the next question is suppose you have in row you have a whole bunch of sets of ordered pairs, and then in here you have a DD, and then a bunch of other stuff, and nowhere else in here is a D related to anything else. And the question is, how do you do this on the Hassel diagram? And the answer is, it's just D all by itself that's not related to anything else.
You do the other thing, and then you just put D off to the
Yeah.
How do you know the levels, too?
Now, see, the thing of it is that the levels have significance. The elevation does have significance. So in a Hassel diagram, if you have one element here and another element, well, wait a second. I should say the elevation only has relevance if they are related. So here, you know, if this one is A, if this one is element A and this one is element B, you know that A is related to B like this.
Right.
Are you with me? But then if you have like this example over here, if there is a D, that D could be up here, or it could be, and there's nothing, or it could be here, or, it could be here. And in that case, the elevation really doesn't matter because D isn't, the elevation only matters if there's a relation line. Did you have another question?
No, he asked if I had two B's, but it was like, I was...
Oh, he said part B instead of element B. Okay, well, anyway. Yeah, okay, these are good questions. Yeah. I hope that you actually looked at the ones that we're going to be due today, because when we actually cover that material, you'll say, oh, that's what that is, and you won't have any questions.
I have a question though. When you're saying the ordered pairs of a given diagram, are the reflexive elements always in it then?
Good question. Now tell me, and can you tell me what? Here, remember what we had. Hold on. Yeah. Equivalence. Okay, so equivalence. Equivalence is R what? RST, and a partial order is what? Yeah. Is RAT. Reflexive anti-symmetric. So reflexive. So answer?
Okay.
Yes.
Does that mean I have to put it on the transfer too?
Oh. Yes.
That could be really, really long.
When you add the reflexive,
It's because it's transitive. It's transitive. So if you have AB, if you have ordered pair AB and ordered pair BC, you gotta have order AC.
adding in reflexive elements you don't have to add anything else to make it transitive.
If you add
because if you have 1, 2, and then you add in a 2, 2, the transitivity is still 1, 2, and you already have
but what about all the other stuff?
Yeah, but there might be, that's a good point. If you have 1, 2, and 2, 2, that means by transitivity you have 1, 2, but you already got 1, 2.
5, 6.
Well, yeah, but
you have to have 1, 6, 1, 5.
If you just add in the reflexive elements.
No, because on this first example, they're like, it's A, B, A, C, A, D, B, C, B,
She's right.
and then you add the reflexive, but then you don't have...
You still have to do some transitive ones, huh?
You don't have B, D. No, you do.
Yeah, you have them all. As long as you do the whole, because as long as when you look at the Hassel diagram, you do all the transitive things right there, and then you add the reflexive elements, you shouldn't have to add anything else.
True by man.
Yeah, I think that's a true statement. Okay, now, so at the end of class last time, we had talked about 14.48.2. Let it, right, that's it.
Yes, it's an
Irreflexive, it's an it.
Irreflexive
It's,
chapter.
yeah. Be the reflexive reduction of this rat, okay? And the reflexive reduction is you just take out all the pairs that are reflexive, right? And then our claim here is that if it's not the case that B is rat related to C, not B rat related to C, equivalence either C is it related to B or B and C are incomparable. Now this is kind of an, this is a little tricky to see, but it's kind of an important detail. And so what I want to do is give you an example. 14.48.2 example. And what we're going to do is we're going to refer you to example 1. We numbered those examples last time. Do you remember those? See example 1. And that example 1 was...
Was that the power set?
Yes, it was the power set. So B was the set A, B, C. And the poset was the power set of B together with the subset relation. Okay? So now what happens with the subset relation, the reflexive reduction of this subset relation is the proper subset relation. Okay, are you with me on that? Okay. So what I'm going to do is, let's take a look at 14.48.2. What I'm going to do is I'm going to write down, I'm going to give you two examples. I'm going to write down that 14.48.2 equation. So first of all, let's do this. Let's do not. Now for B and C, we're going to use the set AB is a subset of set B. Are you with me? So this set AB is going to be B, and the set B, this set B is going to be C. We've got letters here. But these are sets, and those are, so you see the B over, the little b over there is the set AB, and the little c over there is the set B. So how do I complete this? This equivales what?
B
Set B,
is related.
well, but in this case it's a what?
Well, it related.
A proper subset of AB or incomp what to incomp? AB.
Do you just have to write that in a set notation still?
Oh yes, absolutely, you bet.
A set of sets. That's why.
Well, the power set is a set of sets, but each one of those elements here is a set. Yeah.
So when you draw diagrams, you have to, the Hassel diagrams.
Well, you remember when we drew the Hassel diagram, we had the empty set here, and then we went up here and we had and this was the set A, right? Remember that when we did that last time? Okay, so now I have a question for you. AB is a subset of B, true or false?
False.
False. So we have not. So on this side we have not. So does everybody see? On this side we have not, false, equivales. Now B is a proper subset of AB. True. Or now are AB and B incomparable?
No.
That's right. They are comparable. In other words, we know that B is rat related. We know that B is a subset of AB. So this is false, right? Now, did this work?
Yeah, it did.
Yeah, it did, because true equivales true. Are you with me? Now, let's do another one. How about we do this one? Not. Now this time we're going to do AB. The set AB is a subset of the set BC. And that would equivalent what?
BC.
Is
Proper subset.
of AB or in comp what? AB BC. Okay, so now what do we have? Now, is AB a proper is AB a subset of BC? So we have not false, equivalence, and now what do we have here? False, because BC is not a proper subset of this. Or, but now what about this?
Has to be.
Yeah, these aren't comparable. If you look at them on the Hassel diagram, there's no way to get from one up to the other, right? If you look at our Hassel, there's no way. Okay, it's not, in other words, AB is not a subset of BC. BC is not a subset of AB, so they're not comparable. So this is or, oh, so they are incomparable, so that's true. And now did it work still?
Yeah.
It still worked. I guess we could do another example where this one is true. Shall we do it? I didn't have that, but let's do it. So what would be a good example?
Yeah.
Okay, A is a subset of AB. Oh, I'm missing a paren here, huh? Equivalence. Now, so now what would this be? AB is a proper subset of A or in comp. So this is
Not true.
not true. Equivalence.
What kind of not is that?
Oh, not
False or false?
false or,
False.
yeah, and it still works.
False equals false.
Yeah.
Which is true.
All right. Woohoo! So so everybody,
Exciting.
everybody gets what it means to be incomparable. Now, do you remember last time? Now, what we're going to do is we're going to do a proof. Do you remember last time we said that an IT relation is asymmetric? We're going to prove that. Proof that an it relation is anti-symmetric. Okay? So watch this. This is a cool proof. You should know how to do this.
Like this.
Okay, so the first thing we're going to do is a lemma.
Which theorem is this?
It's actually not, I was thinking about that. I should put that, I'm not sure that that's even on our equation sheet.
What?
This theorem that an irreflexive transitive relation is anti-symmetric.
I guess you can put it on the test.
Oh, maybe.
What defines it as an IT, not necessarily IAT?
That's what I'm saying.
No, why is it? Why we even call it IT in the first place?
Because why should we impose anti-symmetric on it when we can define it as being irreflexive and transitive, and then proving that if it is irreflexive and transitive,
It anti-symmetric because it's a reflexive reduction, isn't it?
No. This has nothing to do with reflexive reduction. We're saying any relation that is irreflexive and transitive must be anti-symmetric. We could have defined,
Well, that's, yeah, it's because
but you should assume as little as possible and then prove what you can. In other words, why have an axiom? Well, you see what I mean.
why have a set is just A. Meaning set A.
Yeah. Okay. So we're going to prove that now we're going to start by proving a lemma. This lemma is B is it related to C, and C is it related to B, equivalence false. Okay? Does that make sense? If you think in terms of numbers and less than, how can a number be both less than and greater than? All right. So now our assumption now is irreflexive and transitive. Okay, so we're gonna prove that this equivalence false. So here's what we'll do. We'll start with this. We'll start with B is it related to C, and C is it related to B, and this implies by the fact that it is transitive, what? The silence is deafening.
B at C and C at B. I mean, B at B.
Yeah, B is irrelated to B, right? Because if B is irrelated to C and C is irrelated, then that says B is it related to B, right? Okay. But this equals, by virtue of the fact that this is irreflexive, what?
Not.
Yeah, false. Right? Because, is everybody clear on that?
Anti-symmetric because the antecedent's always full.
Yeah. Okay. Now, but we want to show that this equival's false. What have we shown? That this implies false. So there's, I mean, we're not quite there yet. Remember 13.74? You don't remember? Oh, now you of all people should know those numbers. I'm surprised that you don't know which one 13.74. It's P implies false. Equivales. Now, do you remember?
P equals false? That'd be
No. No.
True.
No.
False.
No.
P.
No.
Well, it does equal P, but
No.
yeah, it
Pure
does.
false.
P implies false doesn't equivalent P.
P or false?
No.
It does.
True.
No. All these guesses.
Oh, not P.
Not P. Okay. Okay. Not P. Okay.
Really?
That was a long time ago. Okay.
It's 374. That's why you threw me off.
3.74.
We didn't do 13.
Oh, 3. Sorry. Oh. Oh yeah, you would have known. You would have known if it were 3.74. Sorry, not 30 or 3.74. Okay. So therefore, what do we have? So because this implies false, therefore, what do we have? So we have not this, right? So we have not B is it related to C. So we have not it, B is it related to C, and C is it related to B. Right? Because we showed that this implies false. We showed that this implies false, so that equivales.
Not that.
That equivales not. Okay, so we have this, yeah? But what are we trying to prove? That this equivales false. So how do what?
Oh, that equals
By 3 point what?
equals false. By
3.15. What is it? Not P
not P
equivales P
equals false.
equal. Yeah, good. Equivales false. Okay. So we have B it related to C and C it related to B equivales false. Okay, so that proves that lemma. Are you with me? So now we're going to go on to the main one.
Wait, so if we're ever trying to prove that something equals false, then we can just prove that it implies false?
Yeah. That's another proof technique, huh?
Yeah, it is. We should make it.
We should make it a proof technique. Well, you know, we don't, I mean,
We don't do that.
we don't do it very much. So we could have done it, but I mean, yeah, that's. All right, so here's the theorem that we're going to prove. You know, I should put this on the equation sheet. Oh, for next year. Okay, so it is transitive.
What theorem is this? It's just a theorem.
Is transitive and irreflexive. And irreflexive implies it is anti-symmetric.
Yeah.
So that way we will show that an it is an IAT. All right, so here's our theorem. So now guess what? Guess what proof technique we're going to use? Obviously, that we always use a lot now. Assuming the conjuncts. Assume conjuncts of antecedent. All right, so assume the conjuncts of the antecedent. So we'll start with this and we'll get it to be true, right? We'll get it to equivalent true. Are you with me? So this is anti-symmetric, equals, no, it's pretty formal. Actually, you can tell me what the next step is, right? Because you have memorized for me the definition of anti-symmetric.
For all
Call
B.
this table.
Yeah. Definition table 14.1D is correct. So what is it for all what? BC. For all BC. Yeah. B it C and C it B implies B equals C, right? But this equals, by our assumption
Our lemma.
and our lemma, okay, our assumption that's B, okay, by our assumption and lemma, what?
False.
For all B, C. Yeah, this is false, right? Implies what? B equals C.
It's always false.
But if you have false in the antecedent,
No, what's the assumption?
Oh, right.
It is
We
transitive.
assumed, yeah.
That's why the lemma works.
yeah.
So it's going to be true.
Yeah, so this equals by, what was that one where the false,
It's got to be 3.7 something.
it is 3.70 what?
Right.
Very close, 3.75, off by 1. Okay, and so this is what? For all BC, range true, true. Oh, now this one I hope you remember.
Yeah,
Yes.
18.2.
No.
9 point.
This is the big this is the one that we always used for the sets proofs?
30.
No.
Oh, no, I was thinking empty.
This is the big one that where we said let an arbitrary element. No.
No. I'm looking it up.
Oh, I know, 'cause that's.
No, it doesn't have a name. It's the 9.8 lemma.
Oh,
Oh, what?
what?
This is the 9.8 lemma.
No way.
Yes, this equals
No.
Oh, yeah.
by 9.8. This is the 9.8 lemma. This is, yeah, because, yeah, and this is true. Right? Are you with me? Because, look, let's remember that. You know, whenever we say let V be an arbitrary element and show that blah, 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 well, this is for all B, you know, and we show that's true, then we say, okay, so then for all B, and then we have to go into here and use the 9.8 lemma, blah, blah, blah. Remember? So,
It's pretty wild.
do you see the conceptually? And now, I hope we're not just manipulating symbols now, but do you see conceptually why this is why this 9.8 lemma works
So
for
that's
proving
saying for
sets?
an arbitrary BC,
Exactly.
true.
Yeah. Well, if it's true, then that's true. So then what we do is, you know, we let it be an arbitrary element, and we stick it in the 9.8, and then we.
So if the body's true, then it's true.
Yeah, for all B body true, that's true. That's the 9.8.
It doesn't matter.
That's the 9.8 theorem. But right. But we use this. We use this to prove the 9. You know, when we prove the 9.8 lemma, we're actually proving what's in here, and then we don't have to, you know, go back and do this every time because we did it once. Are you with me? Now, so here is a big summary, you guys, that you should know. We've looked at 3 different. We've looked at. So here we have a summary. We have equivalence. We have a partial order, and we have a quasi order. Okay. So the equivalence, we denote the equivalence with equals. Okay. And this is our ST, and our partial order we indicate by this, yes, and this is an RAT, and this quasi-order, which looks like this, we did an IT, but we proved that it is A, so this is an IAT. Are you with me? So we just finished up the third one of these. So here is our big summary. All right. So we'll put a big box around this. Summarizing these, okay? Now, 14.48.2, you know, I have a proof of this. Case 1, case 2, it's kind of involved. I'm not going to prove it, but it's provable. Will you take my word for it? Good. All right. Now, next thing, there's actually one more kind of thing that's called a chain. Yeah, chain. The reason it's called a chain, a chain is a special case of a...
Linearly ordered set.
Yeah. Take a look at the definition of a chain. The Hassel diagram, so here's 14.15, or 14.50. Okay? It's a special case. It's a special case of a rat relation. Okay? And the reason it's called a chain is because if you look at the Hassel diagram,
It's a straight line.
yeah.
Wild.
The Hassel diagram looks like this.
It's
Now, why do you, can you tell from the definition there on 1415, what does it say? It says for all BC,
B rat C,
B rat C, or,
B rat C.
yeah, C rat B.
okay.
Okay? So what that says is that everyone is related.
Ah,
There's no incomparables, you see?
but one's lower than all the others.
Well, if it's finite, it is. Okay, but if it's the integers and it's the less than or equal to, then there is no smallest. Okay.
Yeah.
How about this? N less than or equals to this poset. What are n? Natural numbers. Less than or equal to. Is this a chain?
Yeah.
It is a chain. Okay? Every number is less than or, every number is less than or equal to, either one number is less than or equal to another one, or the other one is less than or equal to that. Okay, for all of them. How about this? Real numbers. Is that a chain?
Yeah.
Yep. How about this? How about example 1? Not a chain. How about example 2? Do you remember example 2? It's the one where it was divides. Do you remember we did the Hassel diagram for that? It kind of went, it didn't look like this. It had some branches off of it, right? So not a chain. How about 2 more? You see if you can guess this. How about 1, 3, 6, 9, 12? The set 1, 3, 6, 9, 12. And the operation is divides.
No.
Not?
No.
Why not?
Because 6 divides 9 is false.
But what about 9 divides 6?
Still false.
Ah, okay, so not a chain.
Is this over the integers?
No, it's just these specific ones. For example, how about this? 1, 3, 6, 12, 24. 1, 3, 6, 12,
Then that is a chain.
20. Yeah, this over the divides is a chain. Yeah, so 1 divides 3, 1 divides 3. 1 is related to 3, 6, 12, 24. 3 is related to 1, 6, 12, 24. 6 is related to 1, 3, 12. We had, yeah.
They're all related.
Yeah. Okay. Now we get to 14.51, which is this these bounds. Okay, so here we go. Now, did you read through those and try to figure out the meaning?
Try.
Yeah. So now, do we have is the other one?
It didn't.
These are all minimals, and then we have another one that's,
Big
Maximum.
maximums.
And then we have
yeah, and then we have maximal.
upper and lower bounds. And
Yeah, okay. But I think if you get the minimal one, the maximal, it's the same, but it's just in the other, same idea, but it's just in the other direction. Okay, so now, so let's just take a look and see. I think what we'll do for 14.51 is I'll put an example of a Hassel diagram up on the board, and we will consider the definition, and we'll see if these points are minimal or what. All right, so 14.51 examples. Okay, so let's consider this. In the natural numbers with divides, consider this subset. Consider the subset, and our subset's going to be 3, 5, 7, 15, 20. 3, 5, 7, 15, 20. All right? Can we see this on the video? The screen is out, so it seems like you can't see. Seems like you can't see it from up here, but I guess you
3,
can.
5, and 7.
So let's draw. Yeah, let's draw the. So we have. Yeah. So we have 3 here, and 5. 3 and 5 are not related. So here's 3 and 5.
7.
And
Yeah, this is what I'm talking about. Do you have to have like brackets or anything in 5?
no, because these aren't
I asked you that
sets.
earlier, and you told me that I did.
Well, that was that example, and this is this example.
It's because those were sets.
Those are sets. The elements were sets in that example.
No, it's well of ordered pairs.
No.
No. The ordered pairs would be the ordered pairs in that other example would be ordered pairs of sets.
Yeah.
Are you with me?
So they have to be bracketed.
In that
Because
Because this is a homework example. That's it.
we're working with the power set, so.
we were working in that example. We were working with the power set, and so and the operation was subset, and so therefore the elements were
Also.
were sets.
Okay.
But that was that example.
Okay.
Are you with me on this?
No. I'll just ask you that.
Okay. Yeah, because, well, I mean, okay, look, you remember when we did the Hassel diagram of that one where we were dealing with the power sets? Like this was the empty set.
Oh, I
And the-
understand the power set one.
Oh, but that's when you need, and this was set A.
Then you need it.
Yeah,
But these, like on the homework, it has examples. It says the set of A, B, C, and then the relation has the ordered pairs. So it has like A, B, B. So do my A's have to be?
oh, but those aren't set, yeah, that's not the power set. And what's the,
They're elements of a set, but.
right, but in here, the elements are, these are sets of sets.
Yeah, no.
In this example, that's why. Are you with? In one case we have sets, in the other case we have a sets of sets. In one example we have sets, in the other.
Yeah. I think, yeah.
Okay, so here's 3, 5. Okay, so 3, 5. Now, does 3 divide 15?
Yeah.
And does 5 divide 15? Yeah. So what we'd have is we've got 15 here. And is there anything that 3 divides that also divides 15? No. So that means there's, all right. And is there something that 5 divides and that divides 15? No. So we have, are you with me on this? And then what about 20?
20 coming from 5.
Does 3 divide 20?
No.
No. Okay, so this is 20. But 5 does divide 20, and there's nothing in between it. Because we don't have 10 in here. If we had 10 in here, then we wouldn't have a line from 5 to 20. And this 7 can be here. All right? Now, could you tell me what the ordered pairs are?
Yeah. 3, 3, 3, 15, 5, 5, 5, 15.
Yeah, 3, 15, 5, 15, 5, 20. And what else?
3, 3, 15, 15, 5, 5, 20, 20,
7, 7. Yeah, okay? The reflexive ones. All right? Now, let's see the first definition in 1415 which says minimal. Element B of set of S. Element B of S. So notice that here, S is a non-empty subset of this poset. So here is a non-empty subset of that poset, right? Are you with me on that? Mm-hmm. Now what does it say? If no element of S is smaller than B, in other words, if B is an element of S, okay, so first of all, in order for it to be minimal, it has to be one of these, right? And furthermore, for all C in the range that C is less than B, C is not in S. All right, so from that, can you tell me which elements are minimal? Are there any minimal elements?
3, 5, 7.
Okay, so here, 3, 5, 7 are minimal. Does everybody see why? Why is 3 minimal?
Because there's nothing.
Because there's nothing that is lower. There's nothing that's lower than that. You know, nothing is lower than 5. Something is lower than 20. Nothing's lower than 7. All right? So that's what it means to be. Now, what about least? Element B of S is the least element of S if B is an element of S and for all C in S, B is
Less than or
related to C. B is less than or equal to, yeah.
So we don't have a.
Yeah, there is no
That
least
means
element.
there's absolutely just one.
It's the least, yes, okay? So there is no least element. This pen is getting weak.
And it has to be related to everything else, right?
Yeah.
Yeah.
Like in the
It
power
has-
setting, in the power set example.
Yes, yes. In the power set example, the least element would be the empty set. So in this case, there is no least element. For B to be least, it must be related to every element. So suppose we have this, as an example, suppose we have this subset. Consider the subset 2, 4, 6, 8. 2, 4, 6, 8. What would the Hassel diagram look like here?
It would just be.
It'd be-
our operation?
Oh, it divides. Same divides. This is one subset. Suppose we have subset 2, 4, 6. What would the Hassel diagram look like?
2
It'd be-
up to 4.
Yeah, it would be 2,
Yeah, it's split to 4 and 6.
and then it would be up to 4 here, and it would be up to 6 here, and then it would be up to 8 here. Okay, now in this example, what would,
2.
yeah, so 2 is least. Okay, 2, and what about minimal?
Also 2.
Yes, so 2 is minimal, 2 is minimal, and least. Okay, so it's minimal because there's nothing that's less than it, and it's least because it's related to every other one. Now, on these bounds, let me give you an example that's similar to the one in the homework. I'll draw a complicated Hassel diagram, and we'll see, and we'll investigate what it means for these bounds to be. So, are you ready for this? Here comes a complicated diagram. Okay. Consider A, B, C, D, E, F, G, H, I, J, K. A, B, C, D, E, F, G, H, I, J, K.
We got that.
All right. And here's what the Hassel diagram is going to, I'm just going to give this to you. We have A down here. We're going to go boom. 1, 2, 3. Then we're going to have 1, 2, 3. Okay. And then we're going to have 1 here and 1 here. And then we're going to have 1 here and 1 here. And here's how they're going to be connected. This is going to go up to here, and this will go 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 here and here, and here, and here, and here, and here. Okay? So this is, so here's what it looks like, and here's the elements. A, B, C, D, E, F, G, H, I, J, K. Okay, so Write this down. Right, okay, get this down, and then I'm going to pose some questions for you, okay? Based on this Hassel diagram. And if you wanted, it would take a long time, but if you wanted to, you could. Is the ordered pair AH?
Yeah.
It is.
Yeah.
As long as there's some way it can connect.
Yes, yes. How about HA?
No.
No.
No. Okay. All right.
Not symmetric.
How about, okay, here's what I'm going to ask. The lower bounds of S equals IJK are what?
FGC.
Now, so what do you have to do? You know, when you look at IJK, you sort of look at, you know, I don't want to mess up my diagram, but you understand, I mean, think of it as IJK. So here's the subset, right?
You have FGC.
Yeah. So they are FGCDA, close but no cigar. You left one out.
H, F, G.
Not H.
H doesn't go
Nay,
down.
H is not a lower bound. What does it mean to be a lower bound?
For every single C,
Every single C. B is,
lower than C.
yeah.
It's like the empty set or something? Because it said F.
For all of these, it's low. Okay.
Oh,
So
A, C, D, F, G.
A, C, D, F, G. That's what she said. But you're leaving one out. Say it again.
E.
No,
No, because that doesn't connect.
because that doesn't connect. Yeah, that.
Neither does H. Does I?
I.
Because it goes to itself.
It's related to itself. It's reflexive. Are you with me? So there are I, F, G, C, D, A. I, F, G, C, D, A. Those are the lower. Does everybody see now why those are the lower bounds?
So the greatest lower bound is I.
Very good. So the GLB dot S is I. I is the greatest lower bound. Now, how about this? How about a lower bound? Okay, so everyone knows greatest lower bound now. Okay, what about the lower bound of S equals IFG? This is why I didn't want to mark up my thing. Of IFG.
A.
And is that it?
Yeah.
Yes. The lower bound of is only A.
So is,
Now, does everybody see that with that example how that works?
so is there no greatest lower bound in that example?
Yeah, it is. It's A. Okay, does everybody see how that works? And now I assume then that you can carry this over to the exact same thing. Oh, actually, here we have a theorem, 14.52. Every finite non-empty subset has a minimal element. Okay, not necessarily a least, but it does have a minimal. And then here's some interesting things you can think about this. A least element is also a minimal element, but not necessarily vice versa, okay? A least has to be, because it might not have a least, you know, so it can't be vice versa. A least element is also a greatest lower bound of B, but not necessarily vice versa. And a lower bound of B that belongs to B is also a least element of B. So if you think about that, you know, that's true. And then 14.54 is the exact same thing, except it's flipped. Instead of a lower bound, you have an upper bound, and instead of a greatest lower bound, you have a least upper bound, the LUB. So the lub and the glub, greatest. All right. Is everybody good? Okay. So next time, oh, and also I'll say, I'm going to have to say right ahead of time that the homework assignment for Monday is about relational databases. And And we haven't done that yet. We're going to do relational databases on Monday. We'll just take one day. And so that will be due on Tuesday. Okay, so you can rest assured. All right, see you on Monday.